are what you saw, or what you should have seen with your multi-pendulum system, where you had the two pendulums hanging on the flexible rod. If they're equal length, when you get one of them moving, then the other one should start to move. It's physics. It doesn't work quite the way we expect it will. And it's also what you saw with that resonator box, where you had the tuning fork screwed into a hollow wooden box, and you strike the tuning fork and that whole box begins to vibrate, and it amplifies the sound. Same thing that happens with a guitar or anything else where you've got an object that begins to vibrate because of the vibrations of another object. Okay, easy. Now, there are other things that can start to vibrate because of vibrations in the environment. So how many of you... Okay, so sympathetic vibration is where you're transferring energy to a larger object, and it's a forced or sympathetic vibration that we see in a guitar, we see in a banjo, we see in anything like that. Okay, so there is something called a natural frequency, and we very often talk about this sort of metaphorically with, something resonates with me, and you hear an idea and you think, yeah, that is so true. That's an idea that resonates with you. So that idea is kind of at your natural frequency. We talk about natural frequencies with objects. So if we've got a pendulum of a given length, of course we know that pendulum length is closely related to an object's frequency, right? So there is a natural frequency for that pendulum based on its length. Okay, so far so good. We'll just briefly record this. So we've got this natural frequency in this flexible bridge that ended up leading to the creation of a standing wave, which broke the cables, which led to torsion, which led to collapse. And you contrast that with the very stiff deck structure of something like the Brooklyn Bridge, which isn't going to give you enough leeway to create a wave. Now, in places like San Francisco, let's do that in a better color. You have an environmental phenomena which threatens the stability of buildings. What is it? Earthquakes. Yeah. The ground tends to shake. So when the ground shakes, buildings vibrate. And in San Francisco, some of the things they do, for one thing, they literally anchor buildings to their foundations. That sounds silly, but in parts of the country where we don't have earthquakes, you assume that F sub G is enough to hold a building on its foundation. You've got the weight of a building pushing down against the foundation. That's going to hold it there. Well, what if you live in a place where the foundation is going to move side to side? Then suddenly you have to have some way to make sure that that building doesn't literally slide off the foundation and fall over. So there are literally giant bolts that run from a lot of buildings down into their foundation. Okay, so now you've got it attached to the foundation, but when the building moves, guess what? You're going to start a vibration, and you can start a standing wave in a tall building. Yeah, that's not good. So, do you remember we talked about the phenomena where you use something to stop a standing wave, to stop a vibration? What's that called? Starts with a D. Dampening. In a lot of, and I think the Bank America, or I forget, it's one of the iconic San Francisco towers in downtown. They have, in somewhere near the bottom of the structure, I don't know if it's the basement or the first floor, there are a set of massive weights on pendulums. Massive. And they swing freely. Now, when nothing's moving, they're not moving either. However, if the building starts to move this way, which way are the pendulums going to move? That way. And they in effect dampen the vibration. So as the building starts to do its vibration, these will slow it down. And they dampen the vibration of the building, so you're not as likely to have a collapse event. So, okay. You are all equipped with two instruments on your head that channel waves very effectively. Well, at varying degrees of effectiveness. And it's a sympathetic vibration. So a vibration travels through the air, hits your ear, it travels through those channels. It's kind of like a reverse trumpet or trombone. Into those channels, and there are small bones which are free to vibrate. Those bones vibrate freely, and those bones actually cause the vibrations in the membrane and the fluid that are transmitted to the nerves that then go to your brain. If the nerves are damaged, then you can hear all the sound you want. So there's mechanical hearing loss as well as nerve hearing loss. So, if you are missing structures in the inner ear, like the bones that vibrate, and I can't even remember all their names, or the drum that would transmit the vibrations, then you have a mechanical issue. Hammer, stroke, and anvil, thank you. But if you've got all those structures and the nerves are not transmitting correctly to the brain, then you're still not going to get that information. And if you have brain damage in the part of the brain that is interpreting those signals, everything else can be there, and you're still not going to get that information. So it's a rather more complex process than you would think. There are a lot of pieces that have to go right for everything to work correctly. We talked about standing waves in the last chapter, and we talked about standing waves on strings, and we related the length of a string to the standing waves that are possible, and all that's wonderful. And we have some similarities in terms of wavelength and frequency with a wave and a pipe. There are some differences, however, and that's what we're going to start talking about. Probably we'll do that tomorrow, which means we are going to change the date on homework, and that's where we will pick up tomorrow.